But nevertheless, I'm indeed very, very happy to be here. And let me start by asking, how many of you know about NAL? How many of you know about NAL? NAL, let me expand, it is National Aerospace Laboratories located at Bangalore. How many of you know about NAL? Very, very few know about NAL. Let me tell you a few words about the National Aerospace Laboratories. We call ourselves a civil aircraft R&D organization, and our focus is on making civil aircraft. Right now we are attending to the smaller civil aircraft, but later we hope to broaden our activity into the bigger civil aircraft. What I mean by civil, this smaller is 2-seaters, 14-seater, that kind of a thing. But we also do a lot of work for the strategic sector. For example, we have made a very significant contribution to the light combat aircraft, the Tejas aircraft. How many of you know about the Tejas? The Tejas aircraft? Good, nice. So, all the two important components of the Tejas aircraft have gone from NAL. That is the airframe, that is the body, the structural body, a significant contribution from NAL, and the control law. That's another very important activity, particularly for the electronics, for the computer science and associated disciplines. The control law is also a significant contribution of the control law has gone from NAL. So I have been working on the first part, that is the airframe, where the polymer composites are used in substantial measure. The polymer composites, they are used in substantial measure. When I say polymer composites, I refer to carbon composites and glass composites. When I say composite, it is a mixture of the fabric, that is the glass fabric or the carbon fabric, along with the polymer resin. That's what I mean. As you will see later in the slides, I will show you a few products that we make at NAL. Can we move on, Sandy? Yeah. NAL, as you can see, Hansa has been flying in many flying clubs. It's a trainer aircraft. It's used for hobby sport primarily, and the speed is about 300 kilometers per hour. So the maximum speed, 250 to 300 kilometers. It's a slow speed aircraft, and it's a 2-seater. And many of the pilots who have flown the Hansa, they have reported very good handling characteristics. And then the Tejas, this is the fighter aircraft to which we have contributed in substantial measure. And we have a 14-seater aircraft, that is the Saras aircraft. So these are primarily our aircraft programs. Apart from this, we have a lot of research and development activities in various disciplines. It can be structural engineering, it can be aerodynamics, it can be systems and controls, it can be computer science. In various disciplines, we have a lot of R&D activities. Yeah, next slide. So these are our aircraft, and we also have the micro air vehicle aircraft, what people call as drones. We also have that activity. Next slide. So this is the activity that is more closer to my own heart. In the sense, I head these activities directly. I am connected to these products, and one of the important products, which is interdisciplinary. That is mechanical and electronics, communication and all that, multidisciplinary. One of the products is this radome. I don't know how many of you are familiar with radomes. I'm sure you would be, being in the EC department, being in the communication department. Are you familiar with weather radomes and airborne radomes? Have you heard or no? You have heard? Please. If somebody has heard, please tell me what is the airborne radome and what is the weather radome. If you have not heard, I will tell you. Okay, so this is a weather radome, and what you see on the left is a airborne radome. see on the left, the first figure is an airborne radome and this is a weather radome. Now the point is, the reason I am bringing it up here is, see this radome, this is basically in construction, it is an icosahedral. It's a truncated icosahedron, but the beauty is, if you people are using your mobile phones now, just go to Google and type soccer ball, a football. This football is the same construction, because the reason I am telling you this is, see there are several different variants, but one of the most popular variants I brought it here, and this radome we make it at NAL, what you see at the right top corner. This is as large as 50 feet in diameter, and it should allow the electromagnetic transmission. That means the noise reduction should be ideally zero. The noise attenuation should be ideally zero. So ideally it should allow the electromagnetic wave, because this houses the antenna, it houses the radar. So the primary function of the radar is to house the radar. For either it can be for weather purposes or it can be for aircraft purposes. So this is made of polymer composites. And I was telling you about this icosahedron. See, this is made of 20 hexagon panels and 12 pentagon panels. See, the beauty is, you cannot get a perfect sphere with only hexagons. You have to have the, whatever you are seeing the green insertions. You have to have the pentagons in between to complete to get a complete spherical object. So this we can make it as large as 50 feet in diameter. We have these radomes, which would be, as you can see, the width of this room. What would be the width of this room in terms of feet? 35 feet. So it's much larger than this, the radome. And these radomes, we have made about 7 or 8 of them. We have made 7 or 8 of these radomes. This one. So we have made 7 or 8 of these radomes. So we have made 7 or 8 of these radomes, and they are dotting the Indian coastline. See, in fact, some of our radomes in the coastline, they have become tourist attractions. The prominent among them being the one at Cherrapunji. In fact, 2 years back I went to Cherrapunji to install this radome, and this is basically for weather monitoring purposes. And this is the construction. It is identical to a soccer ball. A soccer ball, if you are not aware, it is an icosahedron based construction. They come under the generic name of platonic solids, which is a very important aspect in geometry. It is a very important subject in geometry, platonic solids. So this is one of the examples of a platonic solid, the icosahedron. It consists of 20 hexagons and 12 pentagons, and it is made of polymer composites. So the significance is, you should have a very light structure. If it is very heavy, when you are dealing with such large structures, you have problems in transporting, you have problems in assembly, installation, and all other issues. Because in the outdoor, you don't get cranes, you don't get other material handling equipment, and other installation support is rarely available. That too at remote places. So we have one at Cherrapunji, we have one at Gopalpur, which is an island off the coast of Orissa. We have one at Sriharikota, we have one at Cochin, we have one at Bhuj in Gujarat. Like this, so many places we have these larger domes. So it should be EM transparent, and it should serve the purpose of withstanding severe weather conditions and still perform. Now, this is very important for our later discussion. That's why I am emphasizing on this and I am stressing on this. So these domed constructions, the domed, I will tell it to you again. The domed constructions might lead to domed cities in outer space, in outer planets. So this is the material that could be used to build domed cities. Now I will ask you a simple question. Why should we have domed cities on outer planets? Why not square blocks like the Rajarajeshwari College of Engineering? If you don't know, we will find out later, but I am just posing the question to you. So the cities of the future on outer planets are going to be dome constructions. They are going to be spherical, like you see some of the, like you see for example Vidhan Sauda, or you see the Global Academy of Engineering. They can be seen from miles away. So we will come back to that, why they should be dome constructions. For now we will move on with our presentation. Next slide please. So this is a detail of the Nostra dome. Again, similar construction. It should be EM transparent or it should be selectively transparent, in which case it becomes a smart dome. That means a frequency selective surface. Okay, next slide please. So these are the construction details. We'll move on. So this is our own aircraft. Let's move on. This is what I was telling you. So this is based on, this subscribes to some very fundamental geometric formula, geometric principles. Like for example, the Euler characteristics of the polyhedron. What are the vertices? What are the edges? What are the faces? So the soccer ball is built on a very, very well-defined geometrical principle. This is what you must understand. Likewise, there are. Okay, I think we will stop there and we will come back. Now.